I'll get started here. Let me begin with a word of prayer. So, Dearly Father, we thank you for this day again. I thank you for this class, and just pray you be with us, help us to glorify you what we do, and just have a good semester, Lord. In your name I pray, Lord Jesus. Amen. All right, so before I forget, here is the roster. I have not set up Top Hat yet, but I'll get to it eventually, probably next week. But for the time being, we'll take attendance with this. If your name is not on there, please print it at the end. You just need to check the box. Can we add a date to the first column? Like in the first column, let's make it the, what's today's date? 13th? All right. Well, let's do that then. All right, so let me see if I can, I don't know why it's not coming up there. Well, I must be on the, well, that's HDMI. Come on, thing. Hello. Ah, there we go. All right, so let me just give you the big picture of what I'm doing this semester. I am James Cook. You probably knew that. I think I'm teaching 5 classes residentially and then another one online at the moment, which is a fun story because I thought I was teaching in the second half of the semester, and I found out about 3 days ago I'm teaching the online class this half of the semester. It's a very big difference whether you hear the B or the D. I heard D, but it was B that I agreed to. so, oops. It's fine though. It's all in order now. So you're here, right? So you know what that is. I have office hours from 9:10 to 10:30. Monday, Wednesday, Friday. My office is now in the math department. I got moved out of the interdis mid-semester last time. Let's see here. What else am I teaching? Tuesday, Thursday, I'm teaching the proofs class. Come on, computer. I also have office hours 12 to 2, Monday, Wednesday, Friday. At least that's the plan for now. I'm kind of waiting to schedule a research meeting with a student, so that might push things around. We'll see. But of course, I'll let you know if the office hours change. But for now, that's what they are. I teach physics, of course, from 2 to 3. Some of you have experienced that. Then differential equations, Tuesday, Thursday, and then advanced calculus, which is late Tuesday, Thursday. If you'd like a luxurious classroom experience with lots of space around you, advanced calculus is where you want to be. We got 10 students in there. That room seats like 40. That's the place to be. But it does help to have this class before you take that. So anyway, any questions about my schedule? No? All right, fine. So this is my website, which I think I failed to link in the announcement, but www.supermath.info. Not secure, I don't care. It's because I don't believe in modern HTML, probably. So, I mean, I learned how to make the website when I was in school in the late 90s, and I'm just still doing it, so, you know, whatever. But anyway, you guys are in here. So if you look here, I've got a playlist on YouTube, which is also linked to the announcement I sent you guys. So if you click on that, it'll take us to the YouTube list. Of course, there's nothing there because we can't post the video before I take it. Causality and all. And then this is the course website, which if we click on this right here, will take us to that. The course website has many things. At the top, it's got the course planner. I just gave you a printout of the course planner. We'll talk more about that in a second. I also have the lecture notes. That's a PDF link right there. So you definitely want to get a copy of that and save it on your machine. I think I also posted that in the initial announcement, if I remember right. Those notes are technically from last year, but I haven't changed the course at all, appreciably. It's pretty much the same course with a slight modification. The bookstore would not let me continue using Lay, unfortunately, which is sad because Lay has, the edition of Lay I was using is available for like $20, which is why I was using it. But that's why the bookstore won't use it. So, you know, they say they can't get enough copies of it. I agree, you can't get enough copies of it to make a profit on, that's true. But anyway, so we're using a different book now. And I don't. Did anybody have a copy of the book with them, by chance? No. All right. Well, I thought I would save my trouble of bring it from my office. I see that was a poor decision. But anyway, there's a book. I don't use it too much, but I will talk more about it as the semester goes on. That book is a good second thing to read, and the authors of the book are very careful. So if you need a second opinion on how to calculate something, it's a really good place to look. There's also tons of extra practice problems in there that would be healthy for you to try if you need extra practice. So there's that. The matrix calculator site is really super helpful, especially this part of the course. The number 5 eigenvector calculator, we'll use that later. And then I've just got a couple of PDFs there that are particular comments. Now this down here, these are the 8 required homeworks for the class, missions 1, 2, 3, 4, 5, 6, 7, 8. They're worth 120 points. So let me go to the course planner here. So past this point on the website, down here, there's old quizzes, old tests, old worked examples from other books. But you know what? Linear algebra is linear algebra, so like it's all good. But there's tons of old stuff here. And oh, my art. Let's see here. I was so busy preparing classes this break, I didn't have a chance to do any more art. It's sad. I'm going to get back to it, though. Let me get back to it. Let's see here. Where was I? Oh, yes, course planner. All right, so here's where this is the course planner in color. Exciting, yes? So the structure of my course is pretty simple. Like, you do homework on paper, you write the solutions on paper, you turn it in. And I'm getting rid of homework groups like I had last year because troublesome. So because my experience with the homework groups is that you guys are always leaving the class and it's always a state of flux. And I always have some group that's somehow orphaned off everybody. Like there's just an orphan. It's only the one student who remains. And invariably it's not a very strong student. Somehow they always have the worst luck. So everyone does their own homework. Problem solved. All right. Anyway, so like today we're talking about systems of linear equations, notation, setting up the matrix, hopefully, if I don't waste too much time on this nonsense. And then, we'll be looking at systems of linear equations, the row reduction technique next time. And so this gives you basically the day by day what I'll be covering in here, all right? So like mission 1 is collected. Notice it says collected. It's collected here. It's actually due several days before, so if you want extra time on the homework, the good news is you all have it, right? Everyone has extra time on the homework. It is collected here, but it's due like back up here, just so we're clear. So if you look in Canvas, the due date will always be before, all right? So there's that. Let's see what else can I tell you. Sorry if that's confusing, but that's how it is. There's also this in-class group quiz, which is what it sounds like. So I will give a class exercise the day before the test where you guys can work together on something that's kind of like a pre-test, right? That's where I will pick up any kind of topics I manage to fit into this semester that aren't addressed by these missions for some reason or another. Will probably appear there. And this is probably where you'll end up using the book more than anything else. Like I might actually assign problems from the book in the in-class group quiz. I'll try to bring my book to that class that day, so you can borrow it, but I don't know, I bought a copy of the book for about $50 on Amazon, so, but anyway, you can rent it, I'm sure, electronically for not much or whatever, but, okay, so, any questions? So this is the first in a 2-semester sequence of linear algebra, right? So this is the prerequisite for Math 321, but Math 321 also has a Math 200 prerequisite. So like this class is primarily focused on computation. Now I will ask you guys to do some derivations here and there, like I'll ask you to prove certain things are true, but when I do those kinds of proofs, they're more of a symbolic calculation than they are, the kind of proofs that we'll do in, say, Math 321 if you stay with me for that class. But most of you won't, which is fine. But I will show you how to calculate most everything known to man with respect to linear algebra in this class. So you will leave this class, if you stick with us, with a complete working knowledge of pretty much all the linear algebra you ever could dream of needing to use in industry. All right. So like I worked for the Navy for like a year or so. And so I did, MATLAB and that kind of stuff. And I did have MATLAB projects in this last year, but there's just not, you guys got too much else going on to also do that. So I've cut that out of the course. I hope that's okay. So anyway, so test 1 is focused on like systems of equations and matrices. Test 2, we look at what's called the determinant, and then we also look at linear transformations and how to diagonalize linear transformation. Basically, we look at eigenvectors and so forth. That brings us to test 2. And then the third part of the course, we turn to the question of like orthogonality, and we look at applications to like conic sections, quadratic surfaces, the problem of like maximizing a function of several variables, things like this. So show of hands, who's had calculus 3 in here or is currently taking it? Okay, so if you haven't had it, you're close to somebody who has. So when we get to this stuff, it shouldn't be too mysterious. Like the calculus 3 that I need is partial differentiation. So everybody who's in calculus 3 right now will have partial differentiated to death. By the time you get to this, you'll be so bored with partial differentiation, you'll have trouble staying awake in that section. Anyway, so, and then some of these, so then we have, we study differential equations, like how to solve a system of differential equations in here, because once we have linear algebra, that's easy. And then finally, the course ends with a look at something called the singular decomposition, singular value decomposition, if I can talk. And just maybe one lecture, basically. This one lecture here is on the sort of the high points of Math 321 and how it would be applied in like Fourier analysis, things like that. So that's the course in a nutshell. Notice that there is no in-class test 3. Test 3 is actually a take-home test. So there's 2 in-class tests. There's the take-home test 3, which I think I have not put when it's due, but I'll figure that out. I mean, before the end of the course. Now, this in-class group quiz is important because we do, just because there's a take-home test for this last third of the course, it doesn't mean that it doesn't appear on the final. So you do need some experience with like in-class time pressure questions about this material, and that's part of the reason I have that in-class group quiz, just to kind of give you some experience with that material before you just see it on the final, all right? Because there are appropriate questions to ask in a classroom setting, but at the same time, these particular topics are much better left to sort of an open format with more time. So anyway, any questions? Well, you guys, yeah.
It might be a dumb question, but where do I find the book for the class? I'm not seeing it in the syllabus or anything. Like which book is supposed to be?
Well, if you look at the bookstore, it has it there.
I mean, like, right? But where do I find on the course like which book? Is it listed in Canvas somewhere?
Isn't there only one book in the bookstore? I could be wrong. I could be wrong. All right, this is dangerous right here. LU bookstore. No, I'm curious. I'm curious though. This is a decent question. This is a good question you're asking. Where was I? Let's try it out. Download a PDF. This is not an easy one to find in PDF. You're like challenge accepted. Let's see here. We're in 221, right? Yeah. Let's see here. It should be Svensson. Yeah, there it is. So, elementary linear algebra, classic version. You can get paperback, you can get hardback, whatever. I have a hardback I got from Amazon for about $50. So, yeah, it's the elementary linear algebra. That says a matrix approach there. If you can't really read it, but this is actually by Spence, Inzel, and I thought there's a Friedberg here. Well, anyway, I think they left an author out there, but whatever. If you want to see the book in person, I have it in my office. I just didn't bring it down. Like I said, this is not terribly important for us as things go. Like, it's much more like if you don't buy the book, it's not like a problem. Getting to the point here, as long as somebody around you has it, you know. Need some people with books. So, all right. Where was I? All right. So the book. So you're like, well, don't we need a book? Well, yes, we have a book. It's my notes. So my notes have 300 pages, and they have more detail in some parts than the book does. So my notes are the book essentially in here, and I charge you $0 for it, so it's probably okay. I mean, I also make mistakes, so if you have questions, by all means, email me. By the way, email me. Do not use this Canvas messaging thing. It is horrible, because if you use it, there is no way to reply to you properly in such a way that I have record of it for future email like searches and such. If you just send me an email at jcook4@liberty.edu, I get your email and then I can respond to it like a human. It's nice. Yes?
So are these 300 pages of this why you never typed up our physics notes last year?
Oh no, these have existed for years. Yeah, these are old.
I'm still there.
You're still bitter. Oh. Well, I might type up the rest of the physics notes, at least for mechanics this semester. I don't know. It's possible. Are you talking about Are you still bitter about E&M? Is that it?
No, E&M was so much better about mechanics. You said you were going to type about it, and you just did.
So you're completely, you don't, I didn't write, I didn't. Interesting. What is that? Like, what is this? Why is there camouflage wrapping paper here? I feel like we need to put that up on the wall or something. I don't know. Yeah, sorry. There we go. All right, sorry, I'm easily distracted. Let's get to work here. You put this away. So I'm sure I have forgotten to say something or other about something or other, and I'll probably make an announcement about it later. It is important that you kind of keep an eye on announcements. I do use announcements to communicate things sometimes. So if you have notifications for the course off, then that's not probably wise. All right. So let's talk about what are linear equations. So let me just begin with an example. Actually, I'll begin with maybe, I'm trying to think. I think I need 4 examples here. So let's see here. So example 1 might be something like x minus y equals to 1 and x plus y equals to 2, let's say. All right. So that's a system of linear equations. Another system of linear equations we could look at would be something like, I don't know, x plus y equals to 0 and x plus y equals to 1. I retract my 4th example. And my 4th example would be something like, 2x equals to 3y and 4x minus 6y equals to 0. All right, so we have here 3 systems of equations, and I want to talk about how to understand them. Hopefully you already know how to solve these, right? What are the ways that you would solve them? Any ideas? Yeah.
You solve for one variable and then plug that variable into the other.
Solve for one variable and plug it into the other is one way we could do it. Any other ideas? Yep. Add the equations is another way we can do it. Anything else? That's pretty much it, yeah. So we can also subtract, right? But you're right, substitution's a good method. We'll use that in the next. Oh man, come on. I just got this marker. So if I add these equations, I get 2x equals to 3. So x is equal to 3/2, right? Now we'll use the substitution idea that you mentioned. And so like, if I look at that, which one should I use to find y if I've already found x? You say 2x plus 2? This one?
Oh, sorry, never mind. I misunderstood the question.
I'm saying y equals to what? 2. You say 2 minus x? So that would be from this one, right? So basically I'll use some, there we go, make a mess of it. These markers are trash. I got these out of the new marker bins. Oh well, my bad. Okay, so 2 minus 3/2 is what? That's, come on, marker. 4/2 minus 3/2, also known as 1/2. Well, this is, wait a minute. Maybe that's an old one. All right, so the solution is 3/2, right? Comma 1/2. That's the solution to this system, right? Right. Which is the same as saying x is equal to 3/2 and y is equal to 1/2, right? But we can just express that together as 3/2, 1/2. This pair of numbers right here, right? This solves both equations at the same time. It's a simultaneous solution. If I plug x equal to 3/2 and y equal to 1/2 in here, 3/2 minus 1/2 is 1, check. 3/2 plus 1/2 is 2, check. It solves both equations, right? Okay, great. So how about the second one? Let's use your idea. Let's solve for y. So like y equals to minus x from the first one, right? Then we'd have x plus y equals to what? X minus x, which is equal to 1, right? If I substitute. So like this equation here, you know, substituting the first equation into the second, essentially, what happens? Oh, ow. Yeah, I got 0 equals to 1, which is not true, right? So what does this mean? Yeah, that means that no solution exists, right? At this point, it's helpful for us to introduce some other notation. The solution set, going back to my previous example, is the pair 3/2, comma 1/2. So the solution set, this is kind of silly, you know, because there's just one thing in the solution set, but there it is. It's that single point. Here, no solution exists. The solution set is the empty set. All right. So we have different options in how we discuss the solution to the problem. We can talk about the actual points which solve the system, or we can talk about the collection of all points which solve the system, which is the solution set. And the solution set may be empty. This is the empty set, which you can also write like this if you want. Curly brackets. All right. Now the rule is just this. We did logical mathematical operations on the given system of equations, and we reached an absurdity, right? If that happens, that means that there is no solution, right? Because assuming that there was a solution led us to something which is false, right? Okay, so then how about this one? What happens here? Let's look at this in a slightly different way. Like this, we could solve for y. We get y equals to what? 2/3 x, right? Yeah. And this one gives us y equals to what? So 6y is equal to 4x divided by 6. 4/6 is 2/3. Well, this is very embarrassing. I thought we had two equations, but actually there's just one. So this is the other thing that can happen. So what's the solution in this case? So basically we have x comma 2/3 x comma, yeah, right, 2/3 x is solution for any x in the reals. So as a point of context here, I'll just assume that we're working over the real numbers until we have reason to otherwise work. Truth of the matter is, you could view that as an equation over the complex numbers, or you could view it as an equation over the rational numbers. Like, you got many choices, right? So that's not really apparent from the context without further, context. So the solution set here is actually kind of interesting. It would be x comma 2/3 x such that x is a real number. So this notation I'm just using is called set builder notation, or set builder notation. The way this works is you have your object here and you have your condition over here. The way this is read is x comma 2/3 x. This vertical bar basically is just read as such that. Right. All right, so let's take a step back and understand what's going on here. We could look at this graphically, right? We could look at this graphically. What is the first situation here? Let me take my pair of equations here and just take a step back. And we usually think y equals mx plus b, right? So like y equals to what? X minus 1. Y equals to 2 minus x. So, and I'll use some color coding here in a second. So I've got minus 1 for my y-intercept, slope of 1. And then the other one, I've got y equals to 2 as the intercept, right? And a slope of minus 1. Okay? And what is this? What's the meaning of the solution geometrically? That's where the lines intersect, right? So that point right there is apparently 3/2, 1/2, which seems kind of reasonable up to the limits of my artistry here, right? So if you have skew lines, there you go. If you have skew lines, they intersect somewhere, right? And at just one point. This is all that can happen, right? But there is other things that can happen, because the lines don't have to be skew. They could be parallel, right? And if the lines are parallel like they are here, so if you solve for y, you got what? You got y equals x. Wait a minute. My bad. The other way around, right? You get y equals minus x. And what's this one? Y equals what? 1 minus x. So that's got the y-intercept of 1, so it's a parallel line. And where do those meet? At infinity? Wrong course. Sorry. No, they don't meet. Right? At least that's what Euclid said. So in Euclidean geometry, they don't meet, at least. So anyway, in here, obviously, there is no place where these intersect in terms of analytic geometry in the plane. So that's why the solution set was empty. And this one here, it would be easy enough to forget about, you know, but in this one, you've got, you know, oh man, I can't do slope 2/3. More like that, isn't it, right? So here, you've got, you know, just a single line, right? And it turns out that, you know, what we're looking at, that's it. That's all that happens. There's either a unique solution, there's no solution at all, or there's infinitely many solutions. If we're working over the real numbers or the complex numbers or the rational numbers, this is inevitable. If we have linear equations, this is all that happens. This is all that we have to look forward to. Either a unique solution, no solution, or infinitely many. The two cases, examples 1 and 3, are what are called consistent. So, example 1 and example 3 are consistent systems. Example 2 is an inconsistent system. So I sometimes might ask you, is this, you know, system of linear equations, is it consistent or is it inconsistent? You know, and to explain why. Now, the problem of showing something's inconsistent amounts to arriving at an absurdity given logical mathematical steps. And so it's tempting. If you make enough mistakes, you can always convince yourself something's inconsistent, right? So we are somewhat limited by our, you know, our frame. But let's look at another system of equations here. Actually, before I do that, let me just set the stage here. So generally, you might have something like this: a11 x1 plus a12 x2 plus da 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 plus a1n xn equals to b1, a12 x2 plus a22 x2 a2n xn equals to b2, and this goes on until we get to am1. Oh man, dudes, that is a 1. Sorry about that. x1 plus a22. I should warn you guys, this is 8:15, so I make exciting new errors at this time period that you won't see me make at other times. But so if you see something, say something. Yeah. So what we're looking at here is coefficients a, I, j. For we have 1 less than or equal to I, less than or equal to m, 1 less than or equal to j, less than or equal to n. M as in mommy, n as in nanu nanu. So these are the coefficients of the linear system of linear equations. What we're looking at here, this thing I'm writing out, this is m equations in n unknowns. This is what we'd like to learn how to solve this first week, basically. All right? So all my examples so far have been very silly. They were just 2 equations and 2 unknowns, right? And example 3, it hardly even qualifies as that, right? Almost. So the unknowns here are my x1, x2, da da da, xn, all right? Now in practice, we'll just use x, y, and z, or x and y, if we don't need to, you know, number it. Sometimes we can get away with not numbering, all right? So let's look at an example which is a little bit harder to visualize. Example, let's say here, 4. What if I have, say, x plus y equals to 1, and y plus z is equal to 1 and z is equal to, well, to be boring, 1. Can we solve this? This is 3 equations and 3 unknowns, right? So by the way, I should mention here, the B1 through BM are the so-called inhomogeneous terms. Inhomogeneous terms. The reason they're called inhomogeneous terms is if one of them, even one of them, is non-zero, then the system of equations is called inhomogeneous. On the other hand, if all of the b's are 0, well, that's a homogeneous equation. Homogeneous equations are especially nice because homogeneous equations are always consistent. Because you can always just put all of the unknowns to be 0 and it solves it. Right? Okay. So can we solve this 3 equations and 3 unknowns? What we're going to do is we're going to use sort of an obvious technique, which is called back substitution. So I was a little bit nonchalant. I didn't use any labeling on the first 3 examples. That was not great. We really should label things. So 1, 2, and 3. So labeling helps us keep things in order, right? Okay, so step number 1, this is very silly. So apparently, z is equal to 3. I mean 1 from 3, right? So we're done with that. Yay. From 2, we can see that y is equal to 1 minus z. Right? But what was z equal to? Z is equal to 1. So this is 1 minus 1, which is 0. So therefore, y is equal to 0. So this is called back substitution because we're starting with the last equation and we're substituting back. And then from equation 1, what do we get? Equation 1, I see that x is equal to 1 minus y, right? But we already know that y is 0, so that's 1 minus 0, which is equal to 1. So therefore, x is equal to 1, apparently, right? So what's the solution here? It is 1, 0, 1. Let me just share a little bit of Calculus 3 with you. I don't typically test on this so much, but I think it's helpful just to gain intuition for what's going on in here. And so here's just a remark. If we have ax plus by plus cz equals to d, the solution set is a plane with normal a, b, c. So, like, the picture is something like this. Right. Now, if d is equal to 0, that means that the plane goes through the origin. If d is not equal to 0, the plane does not go through the origin. Simple as that. All right? So every one of these equations that I have right here is simply an equation of a plane, right? We have 3 planes in 3-dimensional space. One of them I can draw. Sort of. Well, I tried. I was trying. I may yet get it, I don't know. It's anybody's guess, but So this is like z equals to 1, right? It's the horizontal plane. That's z equals to 1. It's just a set of all points with z being 1 and x and y are free, right? This equation, z equals to y plus z equal to 1, that equation is the same for every x, right? So basically that is, you know, this gives me z is equal to 1 minus y, which is something like this, roughly speaking. Don't try to make my picture. It's just nonsense. But anyway. And then the other one is y is equal to, what was it? 1 minus x, right? So kind of the same story. I mean, this plane goes on and on. I can't draw them. It's easier for me just to show you. Drawing 3 planes in perspective never turns out well. So here's basically what's going on is, think of like, oh man, you could think of maybe the bottom of my binder as being the z equals to 1, right? The z equals to 1 minus y is something like this. Son of a gun. I should have picked an emptier binder. And then the other equation, the y equals to 1 minus x is something like this, right? And if you look at where all of those planes equations intersect, there's just one point, right? Like here-ish. If I can somehow put that in there like that. Anyway, if you think about 3 planes intersecting in 3 dimensions, you should be able to see that sometimes it could be a point, a single point, right? And that was the situation here. The single point where these 3 planes intersect is 1, 0, 1. What else would be possible, though, geometrically? What if you have 3 planes and all of them have the same normal vector, right? Like you could have z equals to 1, z equals to 2, z equals to 3. They all have the normal vector 0, 0, 1. And yet there's no point in common, so there'd be no solution. Yep. The other thing that could happen is you could have 2 of them being the same plane, right? And then you could have the third equation, the third plane not being the same plane, but a different one, right? Then those 2 planes which are the same plane and the third plane will intersect in a line. That's still infinitely many solutions, right? But when all 3 planes are the same plane, that's also infinitely many solutions, but in a different way. So if you think about it geometrically, the solution set for 3 equations and 3 unknowns either could be a point, a line, a plane, or nothing at all, right? If 2 of the equations, if 2 of the planes are parallel and the third one's not, that's still not a solution because you need all 3 planes to intersect at the same point for it to be a solution, right? So somehow we have to develop algebra which sorts all this out. And the good news is, well, makes us all feel better if we're geometric. This is not how we do applied linear algebra because we can't always even draw the picture. But we can do the algebra. This is, after all, an algebra class. So, example 5. Excuse me. Suppose we have x1 plus x2 equal to 2, x2 plus 2x3 equal to 0, x3 plus 3x4 equals to 2, and finally x4 is equal to 5. So this system has a very nice form, right? Not all linear equations are going to come to us so nice and pretty like this, but if they are like this, then we can solve them by the procedure of back substitution, right? We solve the last one and use it to solve the one before, and so forth, right? And the logic here is the simultaneous solution has to solve all the equations. So we get to use any equation to simplify the other. This obviously, we're done, right? X4 equal to 5. So x3 is equal to what? negative 13. x3 is equal to 2 minus 3x4, which is 2 minus 3 times 5, which, as you told me, is minus 13. So therefore, x3 is minus 13. All right, so then I'm going to work up like this. Okay, so x2 is minus 2x3, which is minus 2 times minus 13, also known as 26. And then finally, x1 is 2 minus x2, which for us is 2 minus 26, also known as minus 24. So put it all together, we have the solution minus 24, 26, minus 13, and 5. So that right there is the solution. So if a problem has this form, all right, where the last equation, we have this structure, right, where the equations at the bottom can be thought of on their lonesome, right? Like this is not coupled, right? This is not coupled to the equation above it. You can solve this by just looking at this, right? But once you know that, and you use that knowledge up here, all of a sudden you've just got x3 plus a number equals 2, which you can solve by itself, right? If you tried to do this the other way, if you tried to start with the first equation and work your way down, it would have looked much more complicated, right? So one of the first orders of business for us is to be wise in the technique that we use. So for a system like this, you can never beat back substitution. So next class, I'm going to teach you elementary row operations, which is basically a way of systematically doing the adding and subtracting that we did in example 1, as well as the idea that you can take an equation and multiply it by a number. And we're going to see that basically you can take a system like that and you can put it in what's called reduced row echelon, the augmented coefficient matrix. We're going to form the augmented coefficient matrix, and we're going to do row reduction, and that will give us what's called the reduced row echelon form of the matrix. And from that, we just read off solution set. So we will look at the story of this next class. It's very simple, but it does require some practice and some strategery, if you will. So anyway, thanks for your attention, everybody. See you next time.